All right, so we just finished the first little chunk of this unit, and that was just dealing with the concept of charge and electrostatics. And again, we hit that way harder in AP Physics 2, but the next chunk, and this is really the main chunk of this unit, is dealing with the actual concepts of the flow of electricity and specifically DC circuits. So we're going to jump into chapter 22 and skip the rest of chapter 20 and the rest of chapter and all of chapter 21. And those are things we hit again in AP Physics 2. And instead, we're going to start to look at a model of current. So we talked about charge, and current is really the flow of charge. So here I have what's a parallel plate capacitor. It's an AP2 topic, but you can think of it just like a battery. Now, if I look at a battery, if I were to draw it, right, there is a positive end of the battery and there's a negative end of the battery. And that's what allows electrons to flow, or allows charge, I should say, to flow. So when I hook up a wire and I just put a wire across the battery, we can observe a couple things. The wire starts to get warm. Why does it get warm? Some of you might even have like clothing like socks or a electric blanket, and that has wires and that allows it to warm up. So we notice that the connecting wire between them gets warm. And if we were to disrupt that wire and put a light bulb in between, we can see that if there's a light bulb, that it glows. And the stronger this positive and negative difference is, the greater that light bulb flows. So in class, we look at, let's look at one battery and how a light bulb works. That's my positive and my negative side. And then let's add a second battery. Sorry for the crudity of these drawings, but we have a second battery. And if I hook up a light bulb for one battery versus two batteries, we get more current and we get a brighter light bulb. So I would actually demo this in class, but I would charge and discharge a capacitor. But as I have more batteries, I will get a brighter and brighter light bulb. So take a look. You can take a look if you want at the circuit construction kit that is linked on the classroom, and you can take a look at and play around with having more and more light bulbs means a brighter and brighter light bulb. I'm sorry, more and more batteries means a brighter and brighter light bulb. So the way that we kind of think about this is the charges that are moving in the wire are called charge carriers. And specifically, those are electrons. And the motion of those electrons flowing, they flow through a conductor because the conductor allows that sea of electrons to flow through it. And the whole metal then is allowing those electrons to flow through that conductor. Now, an insulator does not have free charges and can't carry a current. So when I hook up things like plastic, that's not going to allow electrons to flow and nothing will happen. But those conductors are allowing those electrons to flow. So the way that it happens scientifically is we are creating what's called an electric field. And again, this is a Physics 2 topic. But that electric field exerts a force on the electrons, right? And that's coming back to the concept of Coulomb's law. So I have some type of field exerting a force, and they begin to accelerate. Now that force, I'll talk about it now, I'll talk about it later, is called an EMF. An EMF is an electromotive force. The electric field that's created by a battery or whatever produces a force on the electrons, and those electrons then flow through a conductor. Now there are collisions that happen all the time, and that transforms the electron's kinetic energy into thermal energy, which heats the metal up or allows the light bulb to glow. So if I connect a wire between two terminals of a battery or between two charged plates that have an electric field, the electrons will flow. So the potential difference creates the electric field that drives the current. That potential difference, we see it actually all the time. If I look on a battery, here's my positive terminal, here's my negative terminal, it tells me right on the battery the magnitude of that electric field is 1.5 volts. So all dry cell batteries have a electric field strength of 1.5 volts. Now again, we get way more in electric fields and electric potential and all that in physics too. We don't really need to understand it all to be able to understand the concepts of current. So here again, I have my positive plate, my negative plate. I have a wire connecting the two, and there is a flow of electrons from my negative plate that go up and across the light bulb and go to the positive plate. And it's the exact same concepts that allow batteries to work as well. But what I see is that there are electrons leaving and electrons entering, and the current leaving, or the number of electrons leaving, is exact as the same as the current entering and the number of electrons entering. So there's a constant flow of electrons going across this mini little circuit here. So the light bulb doesn't actually destroy electrons, because that would violate the conservation of mass. And therefore, the number of electrons is not changed by the light bulb, but the light bulb is kind of using some of the energy from it. So every electron that enters the light bulb has to leave the light bulb, otherwise that would violate a conservation of charge. So electrons flow through the light bulb, they're not used by the light bulb. So you can go ahead and take a look at the simulation. Again, this is the construction kit. You can notice it defaults it to right away. When I pull open this simulation and I set up, all you need to do is grab a battery, and we'll be doing this with lab, grab a wire and a light bulb. And a light bulb will have like two little things, and that's a really bad light bulb. And then you grab another wire and connect it off. And you'll see that there are electrons flowing from the positive to the negative. So what happens, and then you can click on the battery, and it defaults to 9 volts, but you can manipulate the voltage on the battery, and you can see what happens as you change the voltage, and see what happens to the brightness of the light bulb. And that gets us to the law of conservation of current. And the law is very simple. The current is the same at all points in a current carrying wire. The current is, again, the flow of electrons. So when I have current, there are electrons that are flowing, and it is the same at all points in the wire. And when you look at that simulation, you see that all the electrons are moving at the exact same speed. So here's a quick little conceptual example. I have two bulbs that are hooked up. Which bulb is brighter? And the answer is, of course, well, the current is the same and the flow of electrons are the same, which means that bulb 1 and bulb 2 have to be equally as bright. And for right now, for our first section, that's all we really care about. Two main concepts, right? Current, we use the letter I, is the flow of electrons, and the current is the same throughout the wires. And that includes the bulbs too, right? The current flows the same through the bulbs as well. So if an electron enters the bulb, another electron has to leave the bulb. So two main concepts with current. We'll be picking up that and talking more about current and describing it and defining it a little better in the next section.